is an explanation video for a paper titled Concept Distillation, Leveraging Human-Centered Explanations for Model Improvement. Clever Hans was a horse claimed to perform complex arithmetic tasks. It was later found that he was simply using his trainer's body language to get cues and was not actually doing any arithmetic. His trainer wasn't aware about this. Deep neural networks can also exhibit such phenomena. For example, in a real-world data set, cows are naturally found at green fields, and a model trained on this might associate cows with green fields. Thus, it is very important to interpret what cues the model is using for prediction. Interpretable AI methods come to the rescue by giving explanations of models in human understandable forms. They open the black box of models and enhance transparency, accountability, and reliability of a model. Humans often think in terms of abstract concepts like color, texture, shapes, etc. Interpretability methods have turned the focus towards explaining in human-centered concepts. Concept-based thinking leads us as humans to better generalization. So the question is, how can we make models learn the desired concepts? In this work, we propose methods to leverage human-centered concepts for model improvement by anti-hoc training. XAI methods quantify the importance given by a trained model to a particular concept. How can we use this feedback for anti-hoc training? We aim to use concepts by our proposed concept distillation method, which enables us to enhance, diminish, or add concepts to the model. What are concepts? Concepts are abstract human understandable representations. Initial concept identification started with grouping images mapped to similar areas in latent space to NLP word embeddings. The recent methods learn concept activation vectors or CAVs, do neuron attribution, etc. Kim et al. Learned the CAVs in the model's hyperplane. For this, they first pass the given chosen concept C and C' from the model to get its activations for the chosen layer L. Then they use a linear classifier to estimate a decision boundary in the model's activation space. Concept CAV is normal to this decision boundary, pointing towards concept direction. Frequency maps use gradients of logic values with respect to individual input image pixels to get the importance given to pixels. As shown on the right, higher gradients means more importance. Intuitively, gradients measure the rate of change. When rate of change of final layer prediction or logics with respect to some pixels is higher, it is intuitive that the pixel is given more focus. CAVs build on these saliency maps and use concept directions instead of image pixels. They find the directional derivative of final layer logics or loss with respect to concept direction. The directional derivative represents the rate of change of logit or loss in the direction of CAV with respect to model activations. They coin it as sensitivity. This sensitivity is calculated for each of class K images to give sample sensitivity. The existing concept-based training methods can be divided into two categories. 1. Methods that condition explicitly on concepts, wherein the concept is first predicted from an image, and this predicted concept is used for task prediction. These methods require architectural changes to the model and need more concept-level supervision, which might not always be available. 2. Methods that move sample activations according to CAV's direction. This method aims to remove artifacts from the model by moving the class sample activations away from CAV's direction. They learn separate CAVs for each class by giving class samples containing artifacts versus class samples not containing the artifact to the linear classifier. They then simply move the activations by class away from CAV's direction by a linear transformation operation. This method has many cons. Needs OOD samples, data samples not containing the artifact. Learns class-specific CAVs in model's activation space. Hence, concepts can be confused with biasing attributes. Has the very high class variance due to class-specific CAVs. We aim to sensitize or desensitize the model using the feedback provided by sensitivity scores. We can minimize or maximize the component to control concept sensitivity. We do this by controlling the cosine angle between the loss gradient and CAV. For C desensitization, we make the vector perpendicular to CAV, align along the decision boundary. For sensitization, we make it parallel to CAV, align along CAV direction. Our proposed concept-sensitive training involves the following steps. Firstly, the user selects layer L for CAV and prototype utilization. Subsequently, CAV VLC is acquired through learning in layer L. Then the concept loss LC is computed by incorporating the CAV VLC and the loss gradient delta O. Lastly, model M undergoes fine-tuning using the concept loss LC in conjunction with the original loss LO. For inference, we do not need any concepts or CAVs and do simple forward pass from the fine-tuned model. Kim et al.'s aim is model interpretability, hence they quantify effect of concept on final layer predictions. But our aim is concept-sensitive fine-tuning of models, and hence it's crucial to measure the sensitivity of intermediate layer sense directly. Hence, we are concerned with question, if any changes in activations are done in intermediate layer, what is its effect on any layer prediction? Calculating the final layer sensitivity is straightforward due to scalar logics and availability of ground truth class labels used for loss calculation, while intermediate layers have multidimensional outputs and do not have any ground truth class activations available for loss. We combat this issue by use of pseudo-class labels called prototypes. For prototypes calculation, first, we pass the class samples from trained model M to get its activations in layer L. Next, we use k-means on intermediate layer class activations to get k cluster centers prototypes. We calculate prototypes loss LP as the average L2 distance of class sample activation from those k class prototypes and use this loss for our intermediate layer sensitivity. Prototypes not only enable the intermediate layer sensitivity calculation but also give a global effect to sample sensitivity. As we know, local methods are sample specific and global are class specific. Conventional final layer classification loss is sample specific and is calculated between predicted logic and GT label. Since the prototypes represent global class features, we are able to give a global sense to the class sensitivities calculations. Our concept loss is calculated as cosine of prototype loss gradient and CAVs from map teacher and is added along with conventional ground truth loss to form final fine-tuning loss. The above is for desensitization of model for concept C. For sensitization, we need to use 1 minus LCX as concept loss. Our training pipeline is shown with prototype space intermediate layer sensitivity. CAV learning in same model can lead to false associations. For example, in color MNIST dataset which has a digit in specific color always in the training set, example red zeros, orange ones, the model learns to associate the color with the corresponding digit. Now, if CAV learning is done over this bias model, concept red zeros is closer to CAV red than red patches concept. To overcome this challenge, we propose to use a teacher model which has knowledge of concepts for CAV learning. For distilling teacher's conceptual knowledge in form of CAVs to student, we map teacher and student activation spaces for concepts. We train an autoencoder which constructs student activations from teacher and back and train it with a joint loss. We then estimate CAVs in map teacher by a linear classifier. This is followed by distillation of the above CAVs via a proposed concept loss. Our framework comprises of concept teacher and student classifier and has the following 4 steps. 1. Mapping teacher space to student space for concept C and C dash by training an autoencoder EM and DM dash purple lines. 2. CAV VLC learning in map teacher space via a linear classifier LC dash blue lines. 3. Training the student model with concept distillation, solid orange lines. We use VLC and class prototypes LP to define our concept distillation loss LC and use it with the original training loss LO to sensitize or desensitize the model for concept C. 4. Testing where the trained model is applied red dotted lines where only student classifier and classification head are used. We show applications of our concept sensitivity based training in debiasing in classification problems and prior induction in reconstruction problem. Debiasing involves removing biases and is typically done by testing on OOD samples. For debiasing, we experiment with several bias datasets as shown. Color-MNIST dataset has trained sample digit classes in certain colors, for example red zeros always, while test sample colors are reversed. Texture-MNIST is a newly introduced dataset wherein texture bias is introduced. Decoy-MNIST has random colored patches associated in different positions to digit, while BFFHQ is a real-world dataset having trained set as young women and old men and thus involves age bias. We show efficacy of our method in table below. Our usage of teacher and prototypes yields best performance. For MNIST experiments, we compare with zero-shot interpretability-based model improvement baselines and observe that a model gives best accuracies. These zero-shot baselines are pixel rule-based and cannot be applied directly to a dataset like BFFHQ involving complex age bias. Hence, we compare with few-shot debiasing models and find our method to be better. Our method is not limited to user-provided concept sets and can work with bias conflicting samples of old versus young example. We additionally get more generalizability due to use of concepts as seen by better results on testing the color-MNIST and texture-MNIST trained models on different test settings. Our method also observes reduction in model sensitivity by decreased TCAV sensitivity scores in addition to improved accuracy and generalizability. GradCam visualizations also demonstrate that our method brings model focus back on digit shapes from biased textures or color. We also show applications of our method and prior induction in a real-world reconstruction problem of intrinsic image decomposition or IID. IID involves decomposing an image into its subsequent reflectance, color, and shading elimination components. By definition of IID, reflectance shall be affected by color only, and shading shall be affected by elimination only. We induce the prior knowledge into system by usage of concept sets involving color changes in scene and elimination changes. We get improvements in metrics, decreased MSE, increased SSIM, improved CSM scores, and clear qualitative improvements as well. To conclude, we successfully do the following. Extend CAVs from post hoc explanations to anti-hoc model improvement without altering base architecture. Use our novel concept laws for concept-sensitive fine-tuning of DNNs. Use concept distillation to exploit the inherent knowledge of pre-trained models as a teacher in concept definition. Extend model CAV sensitivity calculation from only final layer to any layer and enhance it by making it more global by employing prototypes. Benchmark results on standard biased MNIST datasets and introduce a challenging texture MNIST dataset. Show application on severe biases like age. Show application beyond classification. Tackle multi-branch intrinsic image decomposition problem, introducing human-centered concepts as priors. A pioneering concept-based approach in non-classification problems. Our future works can combine with automatic bias detection and concept set definition methods. Show applications to domain generalization and multitask learning problems. Please refer our website for more details of this work. Thank you.